So today we are going to start the next topic, which is nuclear physics. So we all know that every atom will have a nuclei, and nuclei will contain proton and neutron. Except the H atom, every other element will contain proton and neutron. H atom is the only atom which only contains proton. So we know that the Coulomb's law is not applicable within the dimension of nucleus. So for fairly small nuclei, we totally ignore the Coulomb's interaction. But as the size of the nucleus grows, then when the dimension exceeds certain value, then the peripheral, you can say nucleons, do experience the Coulombic repulsion, and that sometimes lead to the disintegration of nucleus as well. So small nuclei are generally stable, but under certain condition, when it is having misconfiguration, like if the number of neutrons and protons are not in the proper ratio, they always disintegrate in order to go into the state which is quantum wise more stable. Okay. So in nuclear physics, what we study is nucleus, and whoever resides inside the nucleus is called nucleons. So let me start with very basic. So we have something called atomic nuclei. So every nuclei we represent by because we do not represent nucleus, we represent the atom by symbol, let's say X, and we put the A as the mass number and Z as the atomic number. Okay. So what A represents? Number of nucleons. So nucleons means, so whoever is inside the nucleus we call nucleon. And there is a reason for it, because neutron and protons are indistinguishable within the nucleus. They get their identity only when they leave the nucleus. Okay. So neutron and proton are indistinguishable. So neutron and proton are indistinguishable within the nuclei, and that is why we just call nucleons. We don't distinguish. And the Z is called the number of protons. So A minus Z is nothing but the number of neutrons. Okay. So every atomic nuclei you can represent like this. And now comes the mass of nucleus. So mass of nucleus, how we represent? So mass of the atomic nuclei, or you can say atom. So what we must subtract from the atom to make it a mass of nucleus? So difference between the atom and the nuclei is only the electron. So if I remove all electron, this is the way of writing mass of this. This is the how to read mass of this value. Okay. So to represent the mass of nucleus, we have to subtract the mass of electron from the uh, atomic mass. You can say that's the way of saying it. This is the atomic mass. Okay. So now comes the first thing called dimension of nuclei. So, nuclear radius. So the size of nuclei is proportional to number of nucleons. So as the number of nucleon will grow in value, the volume of the nuclei will grow. So you can say volume of nuclei or nucleus you can say is proportional to number of nucleons. So volume is proportional to A value. A is the number of nuclei. So you can add volume equals to 4 by 3 pi r cube. You can say R cube is proportional to A. R is proportional to 1 by 3. What am I? R we can write as some constant into A power 1 by 3. And R naught is the radius of H atom. You can say sing order. You can say R naught is the radius of proton itself. Okay. Nucleus. So we know that each atom will have just one single proton as a part of nucleus. So the size of the H nucleus is same as the size of the proton, and that is the value we write R naught. So nucleus is made of protons and neutrons. But what are protons and neutrons made of? So we say that protons and neutrons are made of nucleus made of proton but these are made of quarks and we have two separate quarks, up quark and down quark. So the property of up quark is that it is having charge plus 2 by 3 electronic charge, and the down quark will have the property that it will have charge minus one third of the electronic charge. So now you know that the charge on the electron is not the most fundamental unit. It is the charge on the quarks which is most fundamental. But up to JE level, we will consider the electron to be the smallest charge unit. So a proton is made of two up quark and one down quark. And if you add all charges, you will get the answer. 2 times 2 by 3e minus 1 by 3e will give you e plus e. So we know that proton is positively charged particle. And the neutron is basically made of two down quark and one up quark. So 2 down means minus 2 by 3e, and 1 up means 2 by 3e, and you can see this will be 0. So basically means neutron is also made of charge, but the total charge of neutron is 0, not the, I mean, it is not chargeless completely. You can think neutron as a hollow shell which is filled with in case of neutron, the core is basically positive and the surface is negative. And that is why the net charge is 0. So you can do the inner circle even smaller, the outer is more thicker actually, but yeah, nevertheless, that's the idea. So that is the designing of neutron. Neutron is not absolutely neutral. And what we also need to understand, am I audible to you guys?
Yes.
Yes, sir.
We also need to understand that mass of down quark is on a bigger side than mass of up quark. So mass of down quark is slightly more than the mass of up quark, and that is why, if you remember, the neutron is made of 2 down quark and 1 up quark, and proton is basically 2 up quark and 1 down quark. So the mass of proton and this is the mass of neutron. Which one is going to be slightly bigger? So definitely the mass of neutron will be slightly bigger than the mass of proton, because you can see clearly that the 2 down quark will make the mass heavier. Okay. So the down quarks are slightly heavier than the up quarks, and that is the reason neutron is slightly heavier than uh, this proton. Okay, so that's simple. And this mass difference is very interesting. I mean, very useful also, because a neutron is able to transit into proton within the nucleus easily, because the high mass object can convert into low mass by releasing the energy, and that energy we call the, that is given by the Einstein mass energy equation, delta E equals to delta mc square. So it is easier for neutron to transit into proton, but the vice versa is not easier. I'm not saying it's impossible, but if I want to convert the proton into neutron, then there must be some method to supply the required energy, because you're trying to create some extra mass. So conversion of neutron into proton is a natural phenomenon. This is called spontaneous, and this is also called the beta emission. But if I have to convert the proton into neutron, this is called the positron emission, and this is non-spontaneous. Why? Because in the due process, you're trying to increase the mass of the system. This is called, basically, this is, you'll come to know later on. This is called positron emission, and positron emission is also called the beta plus decay, and this is the beta minus decay. So out of these two processes, the one process is spontaneous. That is, it can occur on its own because of the mass relation. So you're going from the high mass to the towards the lower mass, and so this phenomena is spontaneous. It can take place, and this phenomena is not spontaneous because we need to supply energy by one way or the other way. So there are some ways by which energy must be supplied. So the way to look at a nucleus is the Quarks model. So one should look at the nucleus as a Quarks model, and according to the Quarks model, a nucleus is only filled with many up quark and many down quark, and this you can actually compare with the idea of the spin quantum number in case of atom. So if you remember that, oh, this is a third one. So if you remember that in case of atom, when we use the Pauli exclusion principle, so in a single place we cannot have all the four quantum numbers cannot be the same. So the quantum exclusion principle is equally followed by nucleus also. So in nucleus we don't have proton and neutron kind of thing. What we have is the collection of quarks, and the quarks will have a random configuration, and every configuration of quarks is called one quantum state of nuclei. Every configuration of quarks creates one unique quantum state. Okay, so every configuration of quarks creates one unique quantum state, and therefore a nuclei can have infinite quantum state. Therefore, nuclei can have infinite quantum state. Okay, so they also follow the Pauli exclusion principle. So what we need to remember that even the nucleus follows the nuclei also follows the Pauli exclusion principle. And what it says that either two protons or two neutrons cannot occupy all quantum, cannot occupy all quantum state. I mean, how to say this? Cannot occupy the same state, same quantum state. Let's call it. Cannot occupy all the same quantum state. Oh no, what does it mean? Like if we have two protons So they cannot live with all same quantum state. So if you remember that in case of the box model of electronic configuration, you represent the two electron in a box by opposite spin, right? And the whole idea of representing like this is so that they may have other quantum state same. So the n is same, uh, the magnetic is same, but the spin must be different because if they are living together, they must have some difference in the quantum state. So they cannot have all quantum state the same, and if it is same, then they cannot live together. That is the Pauli exclusion principle. So two protons and two neutrons cannot have all the quantum number state, all the same quantum state, but just okay. So you can see that if we have two protons together and two neutrons together, as per the Pauli exclusion principle, such pairing is not favorable because they cannot have the all quantum state same. So, but if we have one proton with one neutron, they can live together with all quantum states same. So we can say that, but one proton and one neutron can be together with all quantum states same. So nature favors pairing. That is, nature favors pairing. So I mean, if they are living together with all quantum numbers same, then that is accepted by the nature. But if we have two protons, then they cannot have the all quantum states same. So some difference should be there, and because it's very complex, so I mean I will not go into detail because even I don't. Okay, so the nature will favor the pairing. Now, what else nature favors? So if the two quarks, or you can say if the two quarks having the same spin, then we call they are strongly attracted. So the nucleus with same spin, let me write on this here. These are like some properties of nuclei which you need to remember. So we all know that the nucleus is a short range force. So nuclear force is nuclear force is short range force. So they are strong enough, but for very small range of action. So it is up to few femtometers or Fermi. We call it Fermi range. I hope you know femtometers minus 15. Nuclear force is okay. Let's put a heading. Nuclear force. These are properties. Nuclear force. So nuclear force is short range force. It is only acting up to few femtometers. It is independent of charge of nucleus, or charge of, you can say, nucleons, and also independent of separation. So unlike the Coulomb force where you write k q p2 by r squared, the separation does matter. Within the nucleus, such separational thing is not there. Just a minute. Just a moment, guys. Sorry guys, got some urgent call. Are you there? Hello,
Yes,
hello.
Yes.
yes,
Okay. So now, when we talk about the nuclear force, then nuclear force is short range force. It is up to few uh, femtometers to or Fermi. Second part of is independent of charge of nucleon. So nuclear force does not depend on separation. Okay. Also, it does not depend on how much charge the particle or the nucleon have. So whether we have proton or neutron, their charge doesn't matter. The third property that we need to be aware of in this case is two nucleons with same spin angular momentum will be strongly attracted, whereas two nucleons with opposite spin will be weakly attracted. So if they have the same spin, so if they have same spin, you can think this way. So strong and opposite means weak attraction is strong attraction. So there is no repulsion, only attraction, but is strong and weak. Now, if you remember that if we have two nucleons with same quantum state, so nature will not favor the both the proton to be in the same quantum state. So this kind of arrangement is not favorable for two protons or two neutrons, but it is favorable for one proton and one neutron, because if we have one proton and one neutron, then they can have all the quantum states same. So they can have the same spin as well. That is why when one proton comes in vicinity with one neutron, they they attract strongly. Okay. But if two protons come together, then the because they cannot live in the same quantum state, so they have to reverse the spin to live together. They can live together with the same. So strong attraction. Then this is the weak attraction. So two proton coming together will have a weak attraction, and such nucleus will be very weak in terms of stability. So the right number of proton and neutron matters. We'll come to that very soon. And the last point about this is that the nuclear force does not follow any sort of inverse square law. So it doesn't follow inverse square law. So they don't follow anything like that. So now comes the stability of nucleus. Like we can see that the various region that brings the nucleus together. So sometimes we have the strong attraction, weak attraction, and we have some other factors as well. So we'll try to understand that what actually affects the nuclear stability. So we are going to learn something called binding energy and nuclear nuclear stability. So binding energy and nuclear stability. So if we plot the graph, so what is binding energy by the way? So we know that every nucleus is made from its constituent element. Okay. Hello, hello. Am I audible?
Yes, sir.
So we know that every nucleus is made of its constituent elements, that is proton and neutron makes the nuclei, right? So in the formation of nucleus, some mass is lost and the lost mass gets converted into energy, and that energy is given by the as per the Einstein mass energy relation, and that energy we call binding energy. So you can think of that when we create a nuclei from the constituent elements, that is proton and neutron, then there is a defect of mass. So we have something called mass defect. So mass defect is mass of constituent particle minus mass of nucleus formed. So if I represent the this as some atom, then how to write the mass defect? So we have to write the mass of constituent particles. So we can see clearly we have z number of protons. So the mass that we expect is z times mp, and we have a minus z times neutron. Okay. So this is the mass of the constituent, and mass of the nucleus form how to write MaxZ minus. Can you see that? Is this clear? So the mass defect is written like this. So you know that every nucleus with atomic mass number A and atomic number Z will have the mass ZMP plus A minus ZMN. And if I subtract this, we can get this answer. So now the way of writing this is a bit complex. So there is simple way of writing. So there is a tradition of, you can say, convention that the proton mass we always write in terms of mass of each atom. That's the rule. So you will never find a mass of proton mentioned in the question. Rather they mention. So mass of proton we can write as mass of each atom minus mass of electron. This m is the like a function mass of this atom minus me is the mass of electron. So that is how we write the mass of proton. Is this clear? So this we can rewrite as z times mass of H atom plus A minus Z mass of neutron. So they will give you the mass of neutron, but they will never give you the mass of proton. and this turns out to be so you can see the Me will cancel out, so that Me here and this ZMe will cancel out because this is minus minus plus this. Okay, so you can write as Z times mass of H atom. Uh, so writing this way will eliminate the need to think of electrons. You can see that you're writing the mass of atom only, and that is good enough. So we can write this way. So the mass defect turns out to be Z times mass of H atom, A minus Z times mass of neutron, and then mass of the atomic nuclei. Like we are writing the mass of atom, this is not nucleus, and this will give you the answer. So that's a small change we need to do. So when you create any nucleus from the constituent element, then there is some mass difference, and binding energy we write as delta F C square, which is the as per the Einstein equation. So the whole term we can write like this. So you can think binding energy is the energy released by the system in order to convert from the constituent element to the nuclei. So when you release energy, it means you create a more stable configuration. So this energy is you can say the amount which you have paid to become nuclei. So anyone who wants to destroy you back to the constituent element, they have to supply this energy. Because to become the nucleus, you have released this much energy, then you have become the nuclei. So if you want to go back to the same nuclei, I mean same constituent structure, then you have to get this much energy from some external source. So the binding energy we can define in two ways. It is the minimum amount of energy must be supplied to the nuclei to break down into its constituent element, or you can say it is the amount of energy released in the formation of nuclei from its constituent elements. So there are two ways of defining it. Okay. You can choose the one. So I can put it, and that is why it's called binding. So it will bind the nuclei together. So you can define it. It is defined as amount of energy, amount of energy required to minimum amount of energy required to break a nuclei into its constituent element, or it is the energy released during the formation of nuclei from its constituent elements. So that's the whole idea. Okay. So it is clear what is binding energy. So you can think both ways. Uh, Now stability does not depend on binding energy. It depends on binding energy per nuclei. So stability of nuclei is proportional to binding energy per nucleon. Like to create a nucleus with a number of nucleons, you may have released a large amount of energy, but what is the value per nucleon? So you can think in this way. Let's say if we have some investment. So let's say you and your friend start some investment and you add a sum of 1 crore each. Okay. So the sharing of each person is 2 crore. But imagine there is a startup with 10 founders, co-founders, and all the 10 invest together 5 crores. So what is the contribution per co-founder? Only 50 lakhs. So the strength of binding depends on how much energy is released per nucleon, not the total energy. Because total energy is misleading. So stability depends on the binding energy per nucleon. And if you plot the graph of binding energy per nucleon versus Z, it turns out to be something like it goes 1, 2, 3, something like this. And the maximum stability, the nucleus which is most stable, the most stable nucleus you will find is iron, which is Z equals to 26. 26, right? Iron is 26, no? Yeah. So the nucleus of iron is most stable, not the iron. Iron is like it gets easily rusted. It's very much reactive. It reacts with atmospheric oxygen. But I'm saying about the nucleus of iron. So nucleus of iron is most stable. Okay. So now, so what are the factors which affect the nuclear stability? So factors affecting the nuclear stability. So factors affecting the nuclear stability. So the first is called volume effect. So if you try to create a big nuclei, then definitely what will happen? It will release large amount of energy. Okay. So we all know that the volume effect is all about being proportional to the number of nucleons. So we know that uh, binding energy will be proportional to number of nucleons. Okay, we don't know, because more the nucleons will come into creating the nuclei, more energy will be released. That is for sure. So the first factor, which is the volume factor, depends on the number of nucleons. So the first factor can attach some constant into it. So this is how we uh, write. And therefore, the binding energy per nucleon due to the volume effect is a constant value, and you can write something like this. The second effect is called surface effect. So surface effect is what? First of all, we need to understand what is surface effect. So let's say if we have a bigger nuclei and the surface nucleons, let's say we have proton here. Of course, we do have neutrons, but I'm not showing it. Now, if you come to the surface is quite away from the center. So it's the farthest point. And the problem with the farthest point is, if you are at the farthest point, then the Coulombic force of repulsion may come into picture. So it is not a desirable thing. Like we know that if the size will grow, then you may exceed the nuclear dimension, and so the Coulombic repulsion may come into picture. So surface effect will decrease the binding energy instead of increasing. It is like a Coulombic attraction repulsion will come into picture, and we know that Coulombic repulsion will have the mutual potential energy by the formula K Q and Q2 by R. If you remember the electrostatics, so surface effect will increase the total energy, which is like decreasing the binding energy, because binding energy is like how much energy you lost, but this will add some energy, so you're losing less. So in a way, you can say that binding energy due to the surface will be proportional to R square, right? And we know that the R is proportional to A power 1 by 3. So this we can write as power 2 by 3. And this will actually create the a different effect. So binding energy will decrease due to the surface effect, which we'll write later on. So B2 will be some constant into A power 2 by 3. So binding energy per nucleon will become how much? Minus 1 by 3. Correct? So the binding energy per nucleon, the surface effect will decrease. Okay. So the decrease in binding energy per nucleon, you can write like this, will be this much. The next effect is called Coulombic effect. And you can think this way that every proton may have some interaction with the other proton. Of course, the nuclear force will be the most dominating, but two protons may have some potential energy, or you can say mutual potential. So if we have a nucleus AXZ, so we have basically Z number of protons. Okay. So we have Z protons in the volume of nuclei, and they might be interacting with each other, and they have charge. So generally, what we assume that the binding energy, the Coulombic effect, we assume as proportional to, or you can say decrease will be proportional to the number of possible interaction. You can add Z into Z minus 1 by 2, something like this, a rough estimate. and every interaction will create the energy E square by R. R I am taking the radius of the extreme. Okay. So it's like we just taking the something like mean. So if you talk about the protons, so the closest proton can be at a zero separation, and the farthest proton can be at 2R separation. So we define the mean separation. So mean separation we define as a minimum plus maximum by 2, something like this, which turns out to be R. So we take R as the mean separation, the average separation between the various protons, and this is how we write. And therefore, the binding energy per nucleon turns out to be some constant that's called A3. And okay, I'll ignore everything. I will take as constant. Or you can, if you want, you can write this Z into by 2 E square by R A3 Z into Z maximum E square by, and R we can write as R power, sorry, A power 1 by 3. This is A. So this becomes A3 minus 4 by 3, right? But I think A3 into E square we can keep as constant. Generally, it is written like this: A3 is Z into Z minus 1. They just write some value, they ignore some value. Right? So, and there are many other factors. So, this is up to JE, we only study the 3 factor, but we can have more factors also. So, binding energy per nucleon, we write as A1 minus A2 A power minus 1 by 3 and minus A3 into Z into Z minus 1 by 2 into A power minus 4 by 3. So the number of nucleons, the volume effect will grow the binding energy, but other effect will decrease it. So the total binding energy per nucleon is a function of various things, as you can see here. So this is the binding energy uh, per nucleon. Okay, and the way to derive the formula is like that one. So let's solve one question. So we know the Einstein formula delta equals to delta mc square. So if delta m is 1 AMU, atomic mass unit, or you can say one unified mass unit, 1 U. So what is 1 U? So 1 U is roughly 1 point, how much? I don't remember. 1.617 per minus 27. Is this value? I don't know. How much is 1 AMU? Anybody? One atomic mass unit is how much?
Correct, sir.
Pardon?
Sir, correct.
This is the right answer. No?
Yes, sir.
So the delta E turns out to be 1.67 into 10 power minus 27 into 3 3 are 9 into 10 power 8. This is in Joule. And generally, we write the answer in terms of electron volt. So we have to divide this number with 1.6 into 10 power minus 19. This is EV now. Because 1 EV is minus 19 Joule. So, sorry. Delta E turns out to be, if you divide this, what you get? Let me calculate. 1.67 into 9 divided by 1.6. It's roughly coming in 9.393 10 for 10e. So just a minute, let me check. Oh, this is 16, right? Made a mistake. This is how much? 11. This is how much? 8. My mistake. So delta E turns out to be 939.375 10 power 6 EV. Just so delta E we can write as roughly 939.375, and we write as mega electron volt. So the energy of the nuclei is in the mega electron volt. Now this is the calculation we are getting, but in examination, what is the value which they take, or they will generally mention the delta E is roughly equals to 931.5 mega electron volt. That is energy released by one this. So there is another unit of writing the uh, yeah. So we write 1 U is equivalent of 931.5 mega electron volt per C square. So this is the mass and energy conversion formula. And why this is important? So let's say in a, if you know the mass defect, so 1 is this much. So any value of mass defect in AMU, if multiplied with 931.5, it will give you the answer in mega electron volt directly. So you could just calculate the mass defect and multiply with 931. That will give the energy release in mega electron volt. Okay. So just keep this in mind. This value is very important. So let me give you one example so that you can just understand what I'm saying. So, okay, this is the question. So calculate the binding energy of alpha particle from the following. Uh, Calculate the so mass of H atom they will give you, and it is how much? And they'll give you the exact value 1.007825 U. And as I said, mass of neutron they will give, but not the proton. So instead of proton, they give H atom. And mass of the helium nuclei or helium atom, you can say. And you have to take one U as 931.5 MEV by C square. Now, how the nucleus of helium is created? So you can write the same formula, right? So the mass defect is how much? So the constituent is we have two protons, so twice the mass of proton, twice the mass of neutron, minus mass of helium, minus ZME. If you remember the, but as I said, this we have to convert into hydrogen. So twice, and this connect as mass of hydrogen minus M. This is two only. This is two because of the Z given is two. You can write twice. So if you do so, you can clearly see this will cancel out, and that's why it is not required. So the mass defect turns out to be twice of the mass of the H atom plus twice the mass of neutron minus the mass of the helium atom. Now we are adding the atom. Now let's substitute the value. So mass of the H atom is 1.007825. Twice mass of neutron is 2 times 1.008655, and this is 4.000260, and we will get positive ones. You can just check. This will be positive. So 2 into 1.007825 plus 2 into, and examination you have to be very careful with calculation because these are very small subtle calculation, and anything will make it bad. This turns out to be 0.03036 U. Now to find the binding energy, no need to solve much. Just write the answer as the mass defect is a unit into 931.5 MeV. That's it. Because delta MC square you will write, and that will give the same answer. So into 930. This is roughly equal to 28.28 mega electron volt. So you can understand this way that during the formation of a helium nuclei, this much energy was released to the surrounding. So if you supply this much energy to the helium nuclei now, it will break back into the constituent protons and neutrons. That's the whole idea of binding energy for a nuclei. Okay. So you can go to next concept, and that is the radioactivity. So what is radioactivity? What is radioactivity? Tell me, guys. Am I audible to you?
Yes, sir.
So what do you mean by radioactivity? So now, if we have a nucleus and if the number of proton and number of neutron are not in right proportion, then the stability will be lesser. So, for example, let's say if we have a nucleus with too many protons, if we have too many protons, then which effect will be bad for the nuclei? Surface effect, right? Coming back to this, if you bring the too many protons, then the Coulombic effect is very bad. It will decrease the binding energy drastically. So this is the Coulombic effect. Surface effect, and this is the volume effect. So presence of too many protons will create the decrease in binding energy per nucleon, because these two factors are basically due to protons only. So a nuclei with say, too many protons is not a favorable, because this will make the nucleus really unstable, because the binding energy per nucleon is very small. And every nucleus will try to increase the binding energy per nucleon. So the whole idea of disintegration of the nuclei is to achieve the greater binding energy per nucleon, or to go into more stable state. So if the nuclei is really heavy, means what? Big atomic mass number. So the A is very large. So generally what happens, I mean, as the atomic number will grow in value, you will see that more than protons, neutron will actually dominate. And the reason why neutron will dominate, because we cannot afford too many protons. Although proton and neutron pairing will support, but too many protons will create the second and third term in the binding energy per nucleon. So the surface effect will grow drastically, and the Coulombic effect, and therefore too many protons is not desirable. So we always prefer too many neutrons compared to too many protons, and there is a ratio beyond which things are not good. So every decay is basically trying to balance the, you can say, the number of protons and neutrons, which can create the best possible quantum pairing in and bringing the better stability. So that is the whole idea of decay, why decay occurs in nature. So if we have any nucleus, and they always look for some ways to uh, attain greater stability, and some sort of there is a natural delay process. So nature even do not know when to make this effect possible. So they do it suddenly out of nowhere. They do one fine day. So let's say right now, if we talk about us, we all are made of atoms, and these atoms are roughly created billions of years back through the Big Bang process. Let's call it. So the atom from which we are made of are not young atoms; they are old atoms, basically. So they are very very old atoms, and therefore they are susceptible to decay. So when the atom lives for some long time, they decay back into something, because the nature is designed such. So nature will always keep on creating a dynamic equilibrium. So atoms decays, nucleus decays, and the purpose of decay is to attain a better stability. But there is a delay in the decay. So decay and delay comes together. It is not always happening. It is like every atom will take some time and then will decay. So when we talk about the radioactive elements, so these elements are made of atoms, of course, and these atoms are very very old, and so the nuclei. So they have already lived a billion of years. Now their time is to decay. Okay. So whenever we could talk about the nuclear decay or disintegration, we talk about the old atoms. So they have been living for long, long time, and now they have old enough to decay. You can think this way. The whole purpose of decay is to attain greater stability. There is no other reason. Okay, and every decay disrupt the nuclear quantum state, and that is why when some decay occurs, then within the nucleus we kind of change the number of up quarks and down quarks, and these up quarks and down quarks tries to reconfigure themselves for the better quantum state and more stability. So some of the down quark which is heavier may convert into up quark, or some of the up quark under some circumstances may convert into down quark, and this interconversion always changes the quantum state and so the energy state of the nuclei. So during the like a decay process, let's say if there is alpha decay, when alpha particle is released suddenly from the nuclei, the nuclei will actually go into the high energy state, or you can say more unstable state, because the whole of up quark and down quark will have some reshuffling, because many are leaving the space and the left out will reshuffle and try to go back to the normal energy state. So every nuclei during a decay first gets excited. That is how we say it. So nucleus will get excited and it will de-excite by reconfiguring the up quarks and down quarks to go to the lower energy state. And the de-excitement of nuclei leads to the decay of something called gamma rays. So gamma ray is basically pure energy. It's the energy because of the de-excitement of nuclei. So in a alpha decay, generally gamma is kind of a byproduct. So alpha decay will first convert the nuclei into high energy state, and the nuclei will reconfigure itself within to go back to the low energy state, and the difference of energy value will be released as electromagnetic radiation, and that radiation we call gamma ray. So alpha ray is not a ray, beta is not a ray. Alpha ray is basically a stream of alpha particles. When we say beta ray, it's a stream of beta particles. But when we say gamma ray, then it is a actually electromagnetic radiation or wave. Okay. So gamma ray is electromagnetic radiation or wave. Understood? Hello, hello, 1, 2, 3.
Yes, sir.
So that is the whole theory of so radioactivity is called the spontaneous disintegration of a nuclei into more stable daughter nuclei. Simply, so a nuclei will break and some particle will be released and a more stable nuclei will be formed. So this spontaneous process is called radioactivity. So we can define as, so what is radioactivity? Tell me. It is a spontaneous. It is the spontaneous disintegration. So it is the spontaneous disintegration of it is the spontaneous disintegration of Okay. So we have to study about the various types of decay. So the first decay is called alpha decay. So we'll start with the alpha decay. Now, when alpha decay will occur, so alpha is basically a helium nuclei, of course. So we can write as plus plus. So when you remove the both the electron from the helium atom, what you left with is nucleus. And alpha decay means this much of proton and neutron will leave the nucleus. That's the whole idea. So the total number of nucleon leaving the nucleus will be 4, out of which 2 will be proton and 2 will be neutron. So when a particle is similar to this helium leaves the nucleus, we call it alpha decay. And alpha decay generally occurs in a bigger size nuclei because the first priority of the big nucleus is to make it smaller. And why we need to make it smaller? Because the nuclear range cannot exceed certain range. So as the size will grow too much, the nuclear range will not be able to hold it, and so that part will decay, which you cannot hold it. So alpha decay will give you the quick response to decrease of size. That's the first priority of alpha decay. Okay, so it occurs in all nucleus. You can mention like this. It occurs in all nucleus with a more than 210. So because of bigger size of nuclei, Coulomb force between nucleus dominates over nuclear force. So in a bigger size nucleus, the Coulomb force will come into picture, and the peripheral nucleons will actually be the victim of Coulombic repulsion, and that will destroy. So this decay helps in reducing size of nucleus. Okay. So we can say so it occurs in order to so it occurs in order to bring all nucleons within nuclear range. Okay. So how we represent the alpha decay? So we have any nucleus we can represent like X, and if there is alpha decay, then the mass number will decrease by 4 units. Okay. So of course it will change to new element. and this new element will have the mass number less by 4, and Z will be less by 2, and then we have the helium nucleus. It is clear? So in every alpha decay, this is like a nucleus at rest, which suddenly breaks into one smaller nucleus plus one alpha particle. And because the nucleus is at rest, so we can talk about the momentum also. So momentum of this will be 0, and this will have the momentum that's called P1 or P alpha. Let's say this is the momentum Pm, the mass of the Y, or Py. That's better. So we have to think of the momentum conservation as well. So the momentum conservation will be how much? P alpha minus Py must be 0. Conservation of linear momentum. So from alpha decay, we generally get the question of conservation of linear momentum. That's very famous. So P alpha is same as Py numerically. And now we define something called very interesting Q value. Have you heard this one? Q value. So Q value is called the total kinetic energy available to the constituent particle. Total kinetic energy available to the constituent. So in a product we have Y and alpha. So their kinetic energy sum is called Q value. And the way to determine the Q value is simple. So how we determine the Q value? Mass of a reactant nuclei. Now that's the difference. Minus mass of a product So helium kinetics, helium atom minus, and then we have to put a bigger bracket into C square. Basically, I don't have space to write, but basically, oh, we can do like this. This is the mass defect, and therefore the Q value is defined as delta M C square. So if you just simplify this, all the electron will cancel out eventually. So it will not be there. This is not required. So now we can in fact relate the Q value with P alpha, the momentum also. So we know that P alpha whole square by twice the mass of alpha plus Py whole square by twice the mass of Y is the total kinetic energy of the system, which we call it Q value. And also the momentum conservation says that P alpha is same as Py. So we can substitute Py So let's say I'm trying to find the kinetic energy of alpha particle itself. If I take common as p alpha by 2m alpha, so what I'll get is 1 plus, and this is nothing but the kinetic energy of alpha particle. And this is easy to write. The mass of alpha is 4 times mass of, and the mass of y is a minus 4. So we can multiply with it. Mass of proton, but the ratio will be same. And therefore, the answer is pretty simple and easy to remember. So K of L alpha will be A upon A minus 4. K alpha turns out to be A minus 4.
Awesome teddy bear.
So you can see that if you know the Q value, I can directly get the kinetic energy of alpha particle, and this is something which you need to remember for examination point of view. So in fact, if you want to know the kinetic energy of Y particle or the what we call daughter nuclei, so when the big nuclei disintegrate into small, we call it daughter nuclei, and this will be exactly 4 upon A because sum is Q. So these are the formula which you need to remember from the uh, momentum and energy conservation. And once you have know the kinetic energy, you can find the velocity if you want. The speed, there's something called the recoil velocity of the nuclei. If alpha particle will go right, then nuclei will go left because the momentum must be conserved. Okay,
Yes.
so this is the part of energy and all. And what you're supposed to understand is so you can find the Q value easily. So this entire term will cancel out. So the most important skill in this chapter is to write delta m. And the way of writing is you first write the equation and then you can convert into nuclei mass, sorry, atomic mass, and we have to express something like this. Okay. So now comes the, okay, if you want, I can write here. So the final Q value which you get is something like this: m a x z minus m minus 4 2 minus 4x. That's and no need to worry again. This is easy to calculate because this is we can get in AMU and we know the formula. You know, one U is 931.5 mega electron volt by C square. So you just need to substitute find the difference of masses like this and then substitute the value. You can get the answer easily. Okay. So now comes the beta decay. So beta decay will have three categories actually. So we have something called beta minus decay. We have something like beta plus decay, And then we have something called K electron capture. So we have three methods, and what happens we need to understand. So when someone says beta decay, you have to take care of all three cases. By default, is nothing. So we have to take beta minus and beta plus and K electron capture as well. Now there is a kind of competition between the beta plus and K electron capture, and we'll come to that. What is the meaning of competition? In a beta minus decay, what exactly happens is the nuclei will have more number of neutrons. So let's say a nucleus, the neutron n by p ratio. So let's say generally the neutron upon proton ratio for heavier nuclei should be close to 1.5 for heavier nuclei. The neutron upon proton ratio is roughly 1 for lighter nuclei. You can call it less than 20. So Z less than 20 maybe, or A less than 20. So for lighter nuclei, the N by P ratio we expect is close to 1. For heavier, we expect close to 1.5. But let's say if we have N by P ratio exceeding 1.5, now that's not a good sign. So if this will happen, then it will try to come back to the 1.5 value, and to achieve that, the numerator is neutron. So some of the neutron will convert into proton, and when a neutron will convert into proton, the n will decrease by, let's say, one value, and p will grow, and so they can again reduce the ratio. So this is a phenomena which happens when the n by p ratio is more than desired value, and it will emit one electron, and it will also emit the anti-neutrino in the process. That's very important. This is called anti anti-neutrino. Okay. So in the beta minus decay, we call beta minus because this is the new electron is decaying, coming out, and this electron is called when electron comes out through the nuclear reaction, we call it beta part. So electron orbiting the orbit of an atom is electrons, but when it comes through the, you can say, conversion of neutron into proton, this process we call it beta. This is called beta part or beta decay. And in every beta minus decay, the energy particle is also released, and we call it anti-neutrino, which is just like the electromagnetic wave. So it will have the energy formula H equals to H nu. Nu means frequency. This is the Planck's law. In a beta plus decay, what happens? It's a reverse process. So we are expecting N by P ratio to be close to 1.5, but it is less than that high. Or generally, in case of lighter elements, if the neutron is less than proton, if it is less than 1, so the proton will now try to convert into neutron. Although this is not spontaneous, but within the nuclear cluster, how this reaction happens. So there are various nuclear reactions going on and energy is being released. So these are opportunists. So what they do is they take someone else's energy and create this reaction. So this reaction cannot occur in isolation, but it can occur in a cluster of nucleus, because some reaction is creating the energy and this is absorbing the energy, and that is how it is feasible. So a proton will convert into a neutron and will create a positron particle, which is like a anti-particle of electron with same mass and charge value, but opposite here the sign of charge. And as a result of what will emit is called neutrino. So now this is very interesting. So the particle that will release is called neutrino, and it's easy to remember. You can see here we have minus sign, so the bar is coming, and here we have plus sign, so no bar. So that's how you can remember. The beta plus decay or positron decay, you can say, and the K electron captures are quite close. So in the K electron capture, what happens? The proton of the nuclei, if we have too many protons in the nucleus, let's say we have a nuclei with too many protons. So the attraction is very powerful, and the orbiting electron in the K shell are under threat of this attraction. So because of some reason, the attraction sometimes eats away the K shell electron. It simply captures the K shell electron into the nucleus by pulling it towards the nuclei. So that's why the name is called K electron capture, because you take the electron from the K shell and push within the nucleus, and this happens to convert a proton because you are eating one electron. So when P will take one electron, it will become what? Neutron. And again, in this process also, because these two are same, so beta plus decay is same as the K electron capture, just the way of writing is different. So we also have the neutrino. Okay. So beta decay will have three parts: beta minus decay, which is the regular one, in which the neutron converts into proton. So this is the spontaneous. Now there is a competition between the K electron capture and the beta plus decay. Beta plus is non-spontaneous. That's the problem. So it cannot occur in isolation. So this will never happen in isolation. So as an independent reaction, it is not possible, but it occurs in a cluster of nuclei. So generally, it occurs in cluster of nuclei. That's the whole idea. Okay.
Yes, sir.
But in K electron capture, the energy requirement is not the issue, because we are not converting something lighter into something heavier. Rather, the electron is consumed by the proton and then neutron is produced. Therefore, the K electron capture dominates the beta plus decay in any nuclear reaction. So, K electron capture is more feasible than beta plus decay, but there is some controversy around these two. So, thermodynamically, we can say K electron capture is more feasible than beta plus decay. So, you can just mention this. So K electron capture is more feasible compared to what? Beta plus decay. So beta plus decay is like against the energy. So because in this reaction, we are trying to increase the mass because proton is lighter than neutron. So you can see on the RHS we have extra mass of 2 electrons. Basically, you can look at this. So to create extra mass in a process, we need to supply energy. So this cannot be spontaneous. It cannot occur on its own. We need to have some energy source somewhere which you can consume and create this possible reaction. Okay. So this is the beta decay, and we'll come to the mathematical part also now. So let's start with the one by one. So what is the beta decay? Beta minus. So you can always start with AXZ. If it undergoes beta decay minus decay, so in beta decay, what is happening? Just look at this. You're converting a neutron into proton. So the number of nucleons will be conserved, but the increase of proton will increase the. So Z will be changed to Z plus 1, correct? Atomic number will increase, no?
Yes.
Because what is the meaning of atomic number? The number of protons. So now we have so it will create a new element. A will be same, Z becomes Z plus 1. Okay. So now we have a particle with a zero mass if you balance the A and this must be minus 1, the charge. So we are balancing the mass and charge. So the numerator is representing the mass and the denominator charge, and the electron is having like mass 0. We take a relative mass 0 and charge 1. This is called beta particle. So this is how we represent the beta particle with one energy particle anti-neutron. Okay. So in terms of atom, this we how we represent. In terms of nuclear reaction, this is how we represent. So there are two ways of representing. One is exact reaction, another is what happens if we take some uh, atom and represent the reaction. So you have to be careful like how you're trying to represent. Now this way of representation is important to get the mass defect. Similarly for beta plus decay, the reaction will be, tell me, what we are converting here. So A will never change, but Z will decrease by 1 because we are converting proton into neutron. So if proton becomes neutron, the atomic number will decrease, right? And then what we get is a positron with neutrino. And in the K electron capture, the reaction will be AXZ, and we are capturing the electron, which you can represent as 0 minus 1. So we get a Y, which is A, and Z minus 1 plus neutrino. So this is the way of writing the equation. And what is next you need to write is, can you write a Q value for each case? So I want you guys to write the Q value for each case. Then you can match with my answer. So write Q value for every reaction. What is Q of beta minus? Q of beta plus and Q of K electron capture. Okay. Are you guys trying this question?
Yes, sir.
Call from Mars.